Yeah. So they've just put a lot of pressure on me because I'm recorded. Okay, so I'm going to do a Blackboard presentation. I thought I would be able to squeeze a lot of subject in this presentation, but I think in 1 hour it might be difficult. So there's at least one subject that I want to talk about, is what I call the microscopic approach to n=1 super Young-Mills theories. So that I'm going to talk about for sure. And then if we have time at the end, I'll talk a little bit about the phases of n=1 super Young-Mills theories and relations with Galois groups. But I mean, it's clear I'm going to have very little time to talk about that. So maybe it will be postponed to informal discussions later or tomorrow or whatever. Okay, so let's start with this. So what do I mean by a microscopic approach to n=1? So that's something that, that I've been kind of obsessed with for several years. And the idea is, can we really have some textbook-like derivation from first principles of the exact results that we know in n=1 gauge theories, including, of course, in the vacua or in the phases that are strongly coupled. So not only just like the Coulomb-like type of vacua, where we know very well that we have a nice semi-classical approximation that is exact and we can compute things, but also in the vacua that are strongly coupled and where there's no naive, a priori, simple approximation scheme that could give the result. So for example,
Pure n=1 super.
Exactly. So I was just about to give, of course, so these are the most interesting aspects of n=1. The other case is like very similar to n=2, and that's not so very interesting. The most interesting, as you say, is like vacua, like in pure n=1 gauge theories. Can we compute, So there the question would be, can we compute the gluino condensate from first principles? So there's a huge literature on this subject, but then much more generally, in some very general n=1 gauge theory, can we compute, let's say, the vacuum expectation value of any chiral operator from first principle? And what this, what is the meaning of this, and what are, the underlying, deep things that you have to understand in order to do that. So let me describe first, very quickly, so the kind of theories I'm going to talk about. So they are very general, but I'm going to focus on some specific examples to be concrete. So in any n=1, so you always have, of course, the vector superfield. So that's by definition of n=1, and that includes, so the gauge field and the gluino. Okay, so I will automatically have this multiplet. And then you add matter fields. You add matter, chiral, superfields, and they come in various sets depending on the representation of the gauge group that you want to consider. And a very nice guy is an adjoint chiral superfield. So in all my theories, I will always have an adjoint chiral superfield X, so it's a matrix, an n by n matrix. So, well, the gauge group will be UN in this talk. I talk about some subtleties to go to other gauge groups, but really, UN or SUN, that's essentially the same. So I take an adjoint X in all my theories. If you don't like it, it's not too bad, okay? If you don't like it, you can always put a mass at 3 level and then have this mass goes to infinity and integrate it out, okay? So it's not really a restriction. At the end of the day, you can always eliminate it, but you can see it as a nice technical tool to include it, and it makes things more natural. Then, of course, typically, you want also to include, let's say, some quarks in the fundamental, anti-fundamental, etc. Okay, and that can also be done, straightforward. So that's the kind of theories I'm going to deal with.
That list suggests a relation to n=2 supersymmetry, right?
Yeah. So the fact that you have X makes it look like a little bit n=2 super Young-Mills theories, okay? But at the end of the day, again, I mean, you can integrate it out X and describe things that really, even with X, we shall describe things that are not kind of like n equal 1. Really, again, having this x, I think, is a nice technical device, but it's not restricted. You can always integrate it out at the end and get the results. So it's not, and you'll understand why I need it. Actually, I could formulate the same thing without x, but using, let's say, other fields that would make things less nice. Okay? So typically at tree level, you have a superpotential, and so the superpotential for the adjoint will be completely general. Okay, so you'll have, so the usual conventions here are like this. So I will consider, now an arbitrary tree-level superpotential for x of this form, so polynomial. These operators I'll call uk. Okay, so the uk's are so uk plus 1 here, trace of x to the power k plus 1. So it's an arbitrary tree-level superpotential for x. If I have fundamentals, okay, I can add arbitrary superpotential for these guys, including Yukawa coupling with x of the form, let's say q tilde p of xq, where p is an arbitrary polynomial. So I might do that as well. So that's very standard. Another thing that I will do that is not very standard, but that is actually very natural from my point of view and from the point of view of what I'm going to discuss, is to add as well a generalized term for the gauge kinetic term. So the usual gauge kinetic term is something like this. Okay, so it's like a superpotential, if you like, but in the vector superfield. Okay, and so that's what generates in the Young-Mills action. So you integrate that over half of superspace, that generates the pure n equal 1 Young-Mills action. But of course, in front of this, you have some coupling tau, the usual Young-Mills coupling tau, which in its complexified version is just given by this. Now, for our purpose, it's very natural to consider an arbitrary tree-level term with a coupling that is an arbitrary polynomial in the adjoint field. Okay, in the same way as we've been considering this arbitrary tree-level superpotential for x, then we can consider an arbitrary term like this. It's perfectly well-defined, gauge invariant, etc. Okay, so this will be something like the sum over lambda k over k plus 1, and now I will have, these so-called generalized global operators that appear, and that I call vk plus 1, the generalized global operators. So,
tau is usually.
So tau, sorry, so you will have, and that will be, yeah, so tau, yeah, plus, I need some lambda minus 1 trace w1.
What I was going to say is tau is usually required by positivity of the genetic term to be on the upper half plane.
Yeah.
So generic holomorphic thing will have negative values.
Yeah.
This can only be seen as a formal power series where the lambdas are infinitesimal, right?
Yeah. So you have 2 points of view on that. Either you consider this indeed, as you say, as just turning on some infinitesimal lambda. So like lambda would be like nilpotent elements. You can say that if you like, and I'm perfectly okay with that. That's enough for what I want to do. Or you take that a little bit more seriously, and you define the lambdas in an open set. Then you'll have trouble if you want to compute Kähler terms, because they won't have the usual positivity properties, as you said. But if you just restrict yourself to holomorphic quantities, you don't have this problem. So that's well defined for the chiral sector. But but otherwise you're right. So you can have any point of view, but since I'm interested in holomorphic quantities, this is very natural, and you'll understand why. Okay, so that's the same. So if I didn't have this term, this would be an n equal 2 theories with an arbitrary tree-level prepotential. Okay, the usual prepotential at tree level for n equal 2 is just a quadratic function. Here, this would be an arbitrary tree-level polynomial prepotential. Okay, and that.
If any of those theories exist, you need some. Start with, you need some short distance completion.
So it exists in the chiral sector. It exists. I will define it, and it's perfectly well defined. Okay, so the integrals, the path integrals in the chiral sector are perfectly well defined, and that's the most general setup for Nekrasov formulation of the instanton integrals.
Does that mean something like the topologically twisted version of the theory exists, but possibly the physical untwisted version doesn't exist?
Yeah, you could put it that way. Yeah, exactly. But again, if you don't like that, that's nice because formally you'll have very nice kind of duality that will appear when you exchange the lambdas and the g's in what I will be talking about. So that's why I want to have that. But at the end of the day, you can turn all these lambdas to 0 if you don't like them, okay? And I'm perfectly okay with that. So that's more technical, the technical thing. Okay, so that's the kind of theory that I want to talk about. So, of course, there are many approaches that have been used to study this kind of systems for more than 10 years now. So you have, approaches based on S-duality, based on brain engineering, based on integrable systems. You have a lot of approaches. The most general approach, I would say, appeared in 2002, and that's this digraph-Vafa matrix model, which is equivalent, essentially, to the closed string description of the theory, okay? So that's, I think, an all-encompassing point of view that makes, on a single, in a single formalism, you can understand essentially all that we know. So let me review that, because that's really, in some sense, what I want to justify. So that's, in some sense, what I want to prove is that this closed string description is indeed correct. So let me review that for like about 10 minutes or 15 minutes, and also give you some important subtleties that you have in this formalism. So what is the closed string description? And that's, or the matrix model description, that's really the same. So in the closed string description, you start with the usual. So the closed string description is the geometric transition picture. So that's what I call the closed string description. To derive that, you start from some, D-brain system that generates this kind of theories, and then you apply these rules of geometric transition. The D-brains disappear. They are replaced by some closed string backgrounds with some Ramon-Ramon flex, okay? And since we're interested in the holomorphic sector, the point is that only, if you like, the complex structure of the closed string background is relevant, and that's why you can compute exactly things, okay? And the results of these computations are encoded in a very natural way in a matrix model. So let me use this language because that's very concrete and very natural. So what is the matrix model description? Well, what it yields is just that you compute these generalized global operators in terms of averages over a matrix model, okay? And that works. So this has not appeared before my last paper with this generalized theory, but you can generalize the matrix model to include the lambdas as well. That's perfectly straightforward to do. So what's the result? So the VK, again, so the VK are these guys, okay? These generalized global operators. And so the matrix model tells you that these are averages. So I'm using a double bracket notation to indicate averages in a matrix model, okay? Averages over Hermitian matrices. So this is essentially the formula, except that you have some, okay, so you have to normalize it in this way. Okay, so let's introduce some small epsilon. I'm going to tell you what it is. Okay, so this average means, so the average of trace of xk is in a matrix model. Okay, so you integrate over some Hermitian matrices with a potential that is the superpotential, okay, and you derive by the matrix model partition function. So that's the definition. M is an Hermitian matrix, okay? N by n, so the small n is some dummy variable, and the epsilon I've introduced is something like S over n, where S is some coupling that I will interpret in a moment, and N, so is the size of this matrix M. And you take, at the end of the day, epsilon goes to 0, which is the planar limit of the matrix model. Okay, so that's a recipe, and that gives you the answer for these guys. Okay, it gives you the answer up to some undetermined parameters, the so-called filling fractions of the matrix model, that enter very naturally in the matrix model, because to define the planar limit in the matrix model, you just have to define what the planar diagrams are, and to do that, you have to expand around a particular minimum of this potential. And the most general expansion must be specified by telling how many eigenvalues are you putting in some particular minima of this function W, okay? And the labeling, so the labeling of this number of eigenvalues that you put label the most general planar expansion that you can have, which means that these guys, this VK, will depend so on the number of eigenvalues of the matrix model that you put in the various minima. So they depend on a set of parameters that I'm going to call S. These are the filling fractions. So the S's, if you like, are S1, S. So you have a certain number, SR. These are the filling fractions of the matrix model. And of course, they depend also, let's call G, are all the set of couplings that you had in the tree-level superpotential. So here, okay. And also an epsilon, but when epsilon goes to 0, is 0.
It's actually not necessarily a minima, it's actually an extrema. I mean, it could be...
An extrema, yeah. So solutions, you have to expand essentially, around solutions of this. Sure, it's never a minimum. It's never a minimum, Any extrema defines a well-defined set of Feynman rules, and so a well-defined set of planar diagrams, and that's the definition of what you mean by these integrals. It's not really a matrix integral. It's really the sum over planar diagrams that you define by expanding around the particular solution of this equation that is labeled by this filling fraction. So that's a very precise thing that you have to do. Okay, is that clear? I don't want to spend a lot of time on just to remind you how this matrix model works.
So sorry, that's how you compute the expectation value of those operators in the theory without these things added to the action.
Without what are these things?
Well, so you had your trace.
Yeah, okay. So the statement is that this statement is not changed when you add the lambdas. Okay. So this doesn't change at all. So in particular, the VKs, in principle, here you should have a dependence in lambda.
Yes.
You don't have it. Trust me, I cannot explain. It's not difficult to realize how it works. Okay? So this statement doesn't depend.
In any case, only includes the adjoint chiral field. There's no modification of the matrix model that incorporates this.
No, the matrix model is the same. What is going to change, of course, is the Digraph-Vafa superpotential that tells you what these S are. So the S will depend on lambda at the end of the day. Okay? But at this level, all the lambda dependence is implicit in S. You don't have any explicit dependence, and the matrix model recipe, if you like, is not changed at this level. Okay? So that's the recipe. Now, so these generalized global operators are very natural in this formulation. Okay, so they're given by very simple recipe. Now, of course, you also have the U case, trace of x to the k. Okay, these are a little bit more complicated in this approach, in the matrix model approach. They're not, given straightforwardly in terms of some matrix integrals, but they can be expressed in terms of matrix model data. Okay, and so the result, let me just tell you the results. I should actually write here formulas that are relevant for the matrix model. Okay, so the VKs, are just essentially trace of xk. Okay, so where this means so matrix model. Okay. And in particular, I should have introduced this generating function for the VKs that is identified with the resolvent of the matrix model. through this identification. So that's model, which is just this guy in the matrix model. So that's the VKs. So now let me give you what the UKs are. So for the UKs, I can also introduce like the gauge theory resolvent, so generating function for these guys. Okay. And let me tell you what is the recipe then to compute this. So the result, well, let me take my note because I don't want to try to give you the precise formula. Okay. So the result is like this. So you have a first term that I don't really want to explain what in detail it is, but that's just, planar. This is given in terms of planar matrix model data only. It's very straightforward. So the NIs are integers that you have to fix to describe some particular vacuum of the gauge theory. Okay? So that maybe I should have told you when, so let's show it here. I should have told you when I was introducing the models. So we have this adjoint X, okay? A general vacuum of the gauge theory is described by some particular gauge symmetry breaking pattern of this form. So that's a classical description of the set of vacua, okay? And this integer, so that's just because X at the classical level in a vacuum like this will be, you will have n1 eigenvalues that are equal, then n2, etc. Okay, so that's just the recipe. And so in the Digraph-Vafa recipe, you put these integers ni that you have here classically, you put them here. And this psi I of z are some meromorphic function described on the matrix, defined on the matrix model curves. And so everything is completely explicit. And then there's a modification when you add the lambdas. Okay? So, and that's interesting because when you add the lambdas, this is how the modification works. So you have an additional term. Everybody can read that? Yeah. Okay. That depends. So this V of x corresponds to the lambdas. Okay. To the generalized kinetic term for the glue balls. And so that tells you. So you have to take, the expectation value of the product of these operators, double trace, minus the product of the expectation values. So that the leading contribution to this is non-planar. Okay? So the result is that by introducing the lambdas, you have to deal with subleading large n contributions in the matrix model, and so the UKs, or this R of these, know also about the genus 1 matrix model. Okay, so that's how it works. And you'll understand why I'm emphasizing that, because on the other side of the duality that I want to describe, you'll have something very similar. Okay? So that's how it works. So that's the matrix model recipe here. Fine. So do you have questions so far? Just a very short review of what people knew. So there's one thing that is missing, of course, is that you need to know how you're going to fix the filling fractions. Okay? So for the moment, all these guys, are defined as functions of the filling fraction. So R is a function of Z, it's a function of G, of the lambdas, and of the S. Okay? Same thing for this S. And of course, these filling fractions are just not there in the gauge theory. So you must know what these guys are in the gauge theory to have the answer in the gauge theory. And that's like kind of second part of the recipe in the matrix model. The S's are fixed by considering some particular global superpotential, so this diagram alpha superpotential, that in the closed string theory is identified, with some flux superpotential. So in the closed string description of the theory, these filling fractions are just fluxes. And so you have a Calabi-Yau geometry with fluxes that induces some non-trivial superpotential as a function of the fluxes, and that's exactly the diagram alpha superpotential. Okay, so in the closed string description, it's just the flux superpotential that you have to deal with. And you have to extremize that. And this gives S some solutions, S equal S star, that corresponds, to the actual physical values in the gauge theory. So of course you have to know what this superpotential is. So in the closed string description, again, it's just a flux superpotential, so it's perfectly correct, but it's perfectly elementary. But how do you understand that in the gauge theory setup? Okay, so how do you understand the diagram alpha part in field theory? So the general justification is in two steps, okay? And the first step is to make the link with the matrix model. The second step is then to fix some ambiguity that you have in the diagram alpha superpotential. So what is the best way to understand that? So the first step one is that you derive a set of generalized anomaly equations in the gauge theory. And this is done by considering some nonlinear variations of the fields in the path integral. So for example, in your path integral, you consider this kind of variations for your adjoints, okay? That is generated by some operator ln, which obviously satisfy the Virasoro algebra. Okay, because this is just delta x equals, x to the power n plus 1. You can do the same, but introducing as well this W alpha that you have, that is generated by some Jn that satisfy, this kind of super Virasoro algebra. That is straightforward to check. And by considering this in the path integral, you generate some equations. So let me give you an example. What kind of equations do you generate?
Wait,
So-
why don't the J's commute?
Sorry?
Why don't the J's commute?
So the J's commute because in the chiral ring, if you have, so that everything here is what I'm talking about actually. So this derivation, and I will emphasize that more and more in this talk, this is perturbative. At the perturbative level, in the chiral ring, the W's commute. So if you have two J's, you have four W's, and since they are spinors, it must be 0. That's essentially the argument. Okay, so these are like perturbative relations that you have automatically in the chiral ring that imply this kind of commutation relations. Okay, so if you do the ln, what does it work? How does it work? So ln acting on the operator um, because it's just a derivative, so it just acts in this way. Okay, and ln acting on the VMs is just act in this way. So what did we have? At tree level, we had an action that was just this, okay, that I wrote before. So that was the tree level term, okay? If you vary this with respect to ln, what are you going to get? So you get the variations of the u. So that would be gk uk plus n. And then the same thing here, lambda k vk plus n plus 1. Okay? So that's just taking the variation. Okay, so this term is trace of x to the k plus 1. I'm doing here delta x equal x to the power n plus 1, and that generates this. Okay, so it's a set of equations of motion. So classically, the equations of motion would just be this equal to 0. They're just saying that the variation of the tree-level superpotential is 0. But now, there's an anomaly, and when you do a one-loop calculation, you realize that these nonlinear transformations generate some, like Fujikawa determinant, if you like, in your path integrals, and that produces an additional term. Okay? So here, it's just something like this. That's the term that you have. And so that's the generalized anomaly equation for Ln. Okay? Same thing, so that's generated by Ln. Same thing for Jn. Now for Jn, if you act with Jn on this, you'll get Gk Vk plus n plus 1. If you act with Jn on these V's, you get 0, okay, because Jn, so on um, it's minus n Vn plus m, but Jn on Vm is 0, just for the reason that I was explaining to David before, just for the same reason that you have this kind of identity. So you don't have a contribution from this, and then you have a non-trivial Jacobian in the path integral that generates this term. Okay? So actually, the fact that in this equation, the lambdas do not enter because of this kind of restriction in a chiral ring is at the origin of the fact that this matrix model recipe for the V's is not changed. Okay? Because you see that this is, if you recognize it, this is the loop equation for the matrix model that the lambdas are not entering in this equation. On the other hand, the lambdas are entering in the equation that will determine the U's, and that's why you get this kind of new terms here. Okay, so that's what you have. So this equation, it's an infinite set of equations. It will determine the U and the V's exactly as I have said here. So as function of some parameters S. Okay, so that's the first step. And you make the link with the matrix model, understanding it in gauge theory, if you like. And then how are you going to understand the S's? So the Digraph-Vafa superpotential, the global superpotential, is by consistency completely determined. So it's depending on the G's, on the lambdas, and on the S. So it's completely, so you have, let's say, some zero part that depends. And then you have some one part, that will depend only on S. So I'm extracting from this W Digraph-Vafa a piece that depends only on S, okay? Only on S. And this depends also on G, on the couplings that you have. So this coupling-dependent piece is completely fixed by these equations, if you believe in them. This piece is not fixed, and you have to make assumptions, and the typical assumption is given by some generalized, like Veneziano-Yankelovich form. And if this generalized Veneziano-Yankelovich form is assumed, that then you will find again the results that are consistent with this identification. So essentially, the Veneziano-Yankelovich form is the form that makes this relationship with the closed string formulation consistent, okay? Because the flux superpotential has these Veneziano-Yankelovich terms, if you like. So that's what you have to assume, and that's consistent. Hmm? Depends on the, typically it's just like Ni, Si log Si, something like this. Something like this that you have to add by hand in this approach, which is very, okay. So that's enough for the review. Okay, I'm already very late. So do you have questions on the review? And now okay, so now I'm going forward and trying to say, okay, so what do you have? So now if you want to understand these recipes at a deep, level, at the microscopic level, what do you have to do, and how does it work? So one thing is to understand the anomaly equations. So can we prove at the non-perturbative level these anomaly equations that I have just sketched the derivation at the perturbative level? Okay? this was completely perturbative. These terms are just one loop Fujikawa determinants. So what does it mean to prove that at the non-perturbative level, and what are the loopholes or the weaknesses of the perturbative approach? And so that's very important. And the main idea here is as follows. In the gauge theory, the number of colors, n, capital N, is finite. Okay, we're describing a finite n gauge theory here. This is very unlike the matrix model, where, as I said, you take the planar limit. Okay, so what does that mean? This means that in the matrix model, you find, as loop equations, you find equations that are similar to these ones. But because you're in the planar limit, all the variables that enter the equations are independent, because you're in the planar limit. In the gauge theory, it's absolutely not the case. So the UK, for example, are trace of x to the k. Because x is an n by n matrix, you only have n independent variables, u1 to un. The other ones are given in terms of some polynomial of these n independent variables. Okay? And similarly, the v's, only the v naught up to vn minus 1 are independent, and all the other ones are given in terms also of some polynomials depending on the u's and the v's. So the truth is you have only a finite number of independent variables in your problem in the gauge theory. That's a huge difference compared to the matrix model, and that's a constraint that has been completely overlooked in the literature for a very, very long time. However, it's highly non-trivial, because when you look at these equations, there are an infinite set of equations. Typically, when you have an infinite set of equations acting, that constrain only a finite set of variables, it's not consistent. You have an infinite set of equations for a finite set of variables, it's not going to be consistent. So in the matrix model, it was obvious that it was consistent because all these variables were just independent because you were in the planar limit. But in the gauge theory, it's absolutely not clear that they are consistent because you have these relations. Okay? So now you can prove, let's call that a lemma. If you plug these constraints that you have at the perturbative level, okay, you can very easily compute that precisely, in these equations, then the only consistent result is the classical result. So the lemma is that the anomaly equations plus the above constraints imply that the operator, whatever operator you compute, is just given by the classical. So you don't have any quantum corrections at all. Okay? And that's not surprising, because in perturbation theory, this is just the well-known non-renormalization theorem for perturbative chiral operators. Chiral operators don't have quantum corrections in perturbation theory. We have derived these equations in perturbation theory. We are applying something in perturbation theory, and we find a very complicated way to rederive this non-renormalization theorem. Okay? So really, the perturbative approach doesn't tell you anything about non-perturbative physics, and that's not surprising. So you have to understand the non-perturbative physics associated with these equations, what is really their meaning at the non-perturbative level. So what is the statement? I don't want to erase this equation, so let me write here. So what is the statement? The statement is going to be as follows. So that's what I want to call the non-perturbative anomaly theorem. It will be a theorem in a moment. So the statement is not going to be that you don't have quantum corrections to these equations. As I have said, this is completely inconsistent with any quantum corrections. The point is that the non-perturbative anomaly theorem will tell you that the quantum corrections at the non-perturbative level to the anomaly equations can be absorbed by a proper definition of what we call UK and Vk minus 1 for k greater than n. So it's not that you don't have corrections. It's really, so that's not a non-trivial statement. It's really that at the non-perturbative level, you'll have a lot of corrections. But if you suitably define what you mean by uk and vk for large values of k, then you might absorb the correction into these definitions. And then in terms of these suitably defined variables, the equations will not be changed. And of course, these definitions must be consistent with the symmetries that you have in your problem. So for example, that would mean that the un plus p could have, a form like this, but then they can depend also on the lambdas, these polynomials. So in the case of the standard case, you have only one lambda, which is the instanton factor, q. Okay? So you can have non-perturbative quantum corrections in the definitions of the variables that will be such that you can absorb all the corrections and make the equations look like this. What is very important to realize is that a priori these definitions are completely arbitrary. Okay? They do not correspond to quantum corrections of the chiral ring, which is something that people, that's a statement that people make sometimes, but that doesn't mean anything. So let me just stress that. Okay? So let's consider just the part of the chiral ring that is generated by these n variables. Okay? As a ring, this is just a polynomial ring. Okay? Just consider the most general polynomial in these variables. This kind of ring cannot be deformed. Okay? So that's a trivial mathematical statement. Okay? The polynomial ring in n variable doesn't have any deformation. If you want to go to abstract math, this is related to some cohomology group of the ring, but that's a very elementary statement. You cannot deform the polynomial ring in n variable. Okay? The point is that whatever element in this ring you want to consider, O will simply be a polynomial in U1, UN, and that's it. You cannot deform this statement. Now, what you call UN plus P, of course, is an element of this ring. So UN plus P as an element of this ring is a polynomial in these n variables. Okay? And so it's a polynomial in these n variables. And there's a natural definition at the classical level of what you want to call UN plus P. At the quantum level, since you have, for example, the instanton factor, you might want to enlarge this ring to include the instanton factor as well, which can be viewed as some kind of background chiral superfield, so it's very natural to include it in the ring, and to define this more generally as an arbitrary polynomials on the UNs and the Qs. But this is a definition. You're perfectly good by defining it to be the same as in the classical case. Okay? It's just a choice. It's not any calculation that can yield that. It's a choice. So people who pretend that they compute that doesn't mean anything. It's a choice. You cannot compute it. If you have the feeling that you compute it, it means that in your computation, you've made actually some assumptions that are equivalent to this choice. And that's it. And I will tell you exactly what it is. But so that's a fact. So you want somehow to prove this kind of thing. So one idea that was put forward was as follows. How can you prove that? One possible idea. One idea is that, okay, let's write down on the right-hand side the most general possible quantum corrections that I'm going to have to these equations. Okay, let's write it down, the most general term. And then let's use the Verzumino consistency conditions to constrain these terms, and then maybe show that these terms can be then have this property that they are, they are constrained in such a way that you can indeed absorb them by redefining these U's and these V's. Okay, so that's quite natural. So let me just tell you what it is. So let's call this polynomial AN, and this polynomial BN. because of the algebra that we had before on the L's, you must have relations like this. For example, okay, and other relations. That follows just from the Virasoro algebra, and that's the Vesumino consistency conditions, and you can try to apply this. So that's very complicated, but maybe you can prove that. However, you run into some difficulty. To define the operators Ln at the non-perturbative level, you have to tell how they act on the variables. So for example, how they act on the U's. So the classical level, you had just this because the L's were just corresponding to a variation of the matrix X. Now at the non-perturbative level, you might have corrections on the right-hand side. And if you want to apply this Vesumino type of arguments, you have somehow to constrain what's on this right-hand side. And so a simple guess maybe is to say, okay, the right-hand side is the most general element of the chiral ring with the appropriate charges. And let's use that. That turns out to be wrong. So I'll tell you that the non-perturbative Ln, when they act on UN, on the right-hand side, you no longer have an element in the chiral ring. Which makes this type of arguments completely impossible. And so actually there's a theorem, or lemma, let's call it a lemma, that if you assume that you have these relations and that this is in the chiral ring, again, you can also prove that you don't have any quantum corrections. Okay, so this is just so constrained, actually, that you don't get any quantum corrections. So the true non-perturbative LNs are kind of complicated objects that will act in some rather complicated way. Okay, so that shows that there's really a lot of non-perturbative effects here that are hard to understand with these direct approaches. Maybe a last comment. Why is that so difficult, if you like, to construct the LNs? Let me look at this, because this equation is exactly the loop equation in the matrix model. What happens in the matrix model? In the matrix model, this loop equation is obtained by varying the matrix model partition function, okay, which is just this Coulomb gas of eigenvalue. So in the matrix model, we know the answer. We know what the LNs are, what these operators are. They're just, that's the usual Virasoro operators that act in the matrix model, and they act on this gas of eigenvalue to produce these equations exactly. However, this equation is exact only in the planar limit in the matrix model. Okay, so when you act with the Virasoro operator in the matrix model on your partition function, you find this loop equation plus corrections. But then in the planar limit, these corrections are subleading, you forget them, and you have that exactly. Now the problem that we have to solve in the gauge theory is to find something similar than the gas of eigenvalue, but that is at finite n, that has only a finite number of independent degrees of freedom, and that will, by variation, yields this equation exactly, without any corrections. Okay, so that's the statement here, that you have something that generalizes, the matrix model free energy that has only a finite number of degrees of freedom because you have finite n, and that there's some generalized Virasoro operator that acts on that, and that this generalized thing yields this equation exactly without any 1/n correction or something. So that's what you have to construct. And that's absolutely non-trivial. I mean, if you try to generalize, let's say, the matrix model and that doesn't work at all. It's highly non-trivial that such an object can exist. Okay. So maybe I stop here. I know there are a lot of conceptual issues that I'm mentioning in a very quick way, but questions? Okay. So let me now describe a completely different approach, but I see that I've 45 minutes on this, so I have to be quick. So a completely different approach that a priori has nothing to do with the matrix model, and that will explain everything from first principle. So the idea is a completely different approach. And this different approach is just, you start from the gauge theory path integrals. Okay, so that will be the open string approach, if you like, the open string formalism. And how can you find the closed string formalism in the open string language? So the open string formalism. So how is it going to work? So the idea is to formulate the theory off shell. So I'm going, to compute path integrals off shell, meaning that I insist that the boundary conditions at infinity for the field X is just to be, a matrix with eigenvalues, these AIs, that are external fixed numbers that I'm going to choose at will. Okay? So this is going to give any expectation value as a function of the A's, and of course on the G's and the lambdas. Okay? This kind of path integrals, they are not physical because, of course, the A's are arbitrary. So then you have to find a superpotential for the A's that will compute that. But they are perfectly well defined. Okay? So by doing this procedure, you can compute the UKs as functions of A's, G's, and lambdas. Same thing for the VKs.
You compactify the space.
Hmm?
You compactify the space.
Yeah. Or not necessarily. Then, I'm saying that the limits in all directions is the same. The usual Euclidean path integral.
Well, it's quite important that you don't compactify the space, right?
Sorry?
So that it's relevant to think about definite values for those scalar verbs.
Fundamentally, of course. But then, for the moment, it's the first step. Okay, so I'm an off-shell. It's an off-shell thing. I'm computing this. It's a well-defined problem.
Sorry?
All the infinity becomes a point here.
Oh.
You compactify because you put boundary condition at infinity, just a value.
It's still working in infinite volume, though.
Yeah.
Yeah.
Volume.
Okay,
No,
fine,
but
fine.
this you compactify. It's a topology.
Right.
Okay, so you have this formula. So in some sense, it looks a little bit like the Dijkgraaf-Waffa, the matrix model thing. In the matrix model thing, you are expressing everything in terms of the S's and the couplings. Here, the S's are replaced by A's. Okay, so it's off-shell. It's an off-shell formula. Why am I doing this? The reason is that if you take the A's to be very far from each other, then these path integrals are always weakly coupled. Just because you're off-shell and you can do essentially whatever you like when you're off-shell. So when you're off-shell, you can decide to compute these things in the regime where the path integral is weakly coupled. Just a choice of the region in A space where I compute the integral.
Badly break supersymmetry in those boundary conditions, right?
No.
Because don't you have a superpotential
For A's, yeah. I have a superpotential A.
So you're
That's the
working-
second
you're
step.
choosing to work away from the classical minimum of the superpotential.
Yeah, but that's the off-shell. So that's the ordinary off-shell formulation of quantum field theory. Okay, so you
By
introduce.
imposing that as a boundary condition, right?
Yeah, but the boundary condition is labeled by some kind. So the A's here, the A's should be seen as external background chiral superfield. The A's are chiral superfields themselves. So that doesn't break supersymmetry. Okay? It's a perfectly supersymmetry formalism. There's absolutely no question about it. The A's, so in particular, you can show that these functions are holomorphic in A's. That's one thing. So by going here, so that's very important, okay, to understand that these integrals can always be computed, in some weakly coupled regime, so they are given by instantons. Always. Now, there's this Nekrasov remarkable formalism that allows you essentially to compute whatever instanton integral you want. And how does it work? So Nekrasov, I don't have, I mean, I have only 15 minutes left, so I don't have time to explain what, to make a review of Nekrasov's work, but let's just give you the result. So Nekrasov essentially will tell you that any operator as a function of A, and that's going to be very similar to this, formally similar, is given in terms of some average, but no longer averages over some matrices, averages over a set of colored partitions. Okay? So any operator is going to be the sum of something like this. So I have to normalize, where K, what is K? K is a colored partition. What is a colored partition? It's a collection of n ordinary partitions. So K1 up to Kn are ordinary partitions. And what is an ordinary partition? Well, an ordinary partition, let's call it K alpha, is itself a collection of numbers okay, with the property, that you have these inequalities.
So these are his results for n equals 2.
Yeah. No, I don't have time to tell you how to apply to n equal 1, but trust me, if you're in this regime, you can apply these techniques, and I will tell you how it works. But
You can go to that regime and define those boundary conditions, and they don't work because you're on the Coulomb branch.
yeah, so the question you're asking is, in n equal 2, these A's, first of all, in n equal 2, this would be 0, the V's. And the U's, okay, would not be 0, and the A's would be moduli. Here it's different, okay? Here I'm going to have U and V's that are non-zero. The V's will be non-zero. The A's are not moduli. They are external background chiral fields that I fix by hand. And at the end of the day, of course, I will generate a quantum superpotential for the A's, what I will call the microscopic quantum superpotential. And I will tell you that by extremizing this microscopic quantum superpotential for the A's, I find the full set of vacua of the theory. Okay, but that's in 5 minutes. Okay, so this is how the formalism works, okay, the Nekrasov type of formalism. So you have a sum over colored partition. This is a measure factor. So just to give you some flavor, we have to deal with colored partitions because you have a UN gauge theory. Imagine you take some U1 gauge theory. You say it's trivial, but the truth is that really you have to do non-commutative U1, and I'm going to tell you why in a moment. But let's apply just this recipe to U1, just so that you have an idea. Then any correlator is an average over the set of ordinary partitions. Ordinary partitions are labeled by Young tableau, okay? So any correlator is an average over a statistical ensemble of Young tableau. And you have a measure on the Young tableau here. What is the measure in this case? For ordinary Young tableau, you know that you have a one-to-one correspondence with irreducible representations of the symmetric group. And a very natural measure is just to take the dimension of the irreducible representation of the associated Young tableau. And that's what it is. Okay, so for n equal 1, this measure is just what is called in math the Plancherel measure. It's related. It's essentially the square, to be precise, of the dimension of the representation.
That's your n equals 1 result, or that's Nekrasov?
No, being number of colors, sorry. That's still Nekrasov, okay? Now, for arbitrary number of colors, you have to generalize this measure factor to color partitions. And you have very big, complicated formulas that do that, okay? So let me write now here. Okay, so let me erase this. And let me write the formulas that generalize, well, not generalize, that are similar actually to this, except that no, instead of doing averages over matrices, I'm doing averages over colored partitions. So since I want to be precise, let me give you formulas. So the UKs actually, so I had it. So trace of the UKs are given by trace of x. So I'm using this, I don't know what kind, maybe something like this I should use. So this kind of bizarre bracket means average over colored partitions. You know, I was using double brackets to mean average over matrices. I'm using this bizarre bracket to mean average over colored partitions. Okay? So the UKs are just average over colored partitions of these operators. Okay, of course, I didn't tell you, but this operator on some given partition has some formula, okay, and et cetera, et cetera. So this depends on A, on the lambdas, and now remarkably for the U's, localization in these integrals tell you that they do not depend on G. So it's a statement that is the parallel of the statement here that the VKs in the matrix model didn't depend on the lambdas, only through the S. Here, you know, by exchanging A and S and G and lambda, and U and V, you have a similar statement. The U's will depend on lambda, so the coefficients in the general tree-level prepotential, if you like, and on A's, but not on the G's.
Could you say a little bit about how the derivation, the fact how the instant on calculus is altered by having the superpotential there?
Only for these operators, of course. Then I will tell you that for the V's, that's not the case. Okay? But for this, well, let's talk it this afternoon, because otherwise I don't have time to finish. Okay? It's just technical and not very complicated. It's not a deep thing at the calculational level.
But, sorry, you're claiming that localization still works, even though the fact that your choice of vacuum here is not supersymmetric.
Yeah. Yes. That is perfectly okay. I mean, these are technical details, important, but technical. We can talk more, but I don't have time here to say that to us. So you have this. Then you're going, so you say, in this formalism, the U's are kind of natural. Here, in this formalism, the V's were natural. In this formalism, then the U's, you had some more complicated formula. Here you exchange U and V's, and here the V's are more complicated. So that's something that you have to do. How to compute in this formalism the global superpotential, the global fields, the generalized global fields. And I can just give you the result, and that's what you get. Okay, forget about the factors. That's the formula. So what does that mean? So epsilon is a parameter that you have in these colored partitions, and that needs to be taken to 0 at the end of the day if you want to do field theory, ordinary field theory. I don't have time to explain what this epsilon is. It's not the same as the epsilon that we had in the matrix model. In the matrix model, the epsilon was like 1/n in the matrix model, and it was going to 0. Here I have another epsilon in this formalism. But at the end of the day, I want to take it to 0. Okay? Now you see that the U's were very similar to what you have in n equal 2. Okay, that was Nick's comment, if you like. And you have no problem. You take epsilon goes to 0. They know only about the leading contribution in this Nekrasov formalism when epsilon goes to 0. Now the V's, as you see, they are averages of products minus the product of averages. Very similar, you know, formally similar to what we had here. The V's know about the sub-leading terms in the small epsilon expansion in Nekrasov formalism. So in Nekrasov would say epsilon is the strength of what the so-called omega background. And the global operators know about the first corrections in this omega background. And that's how it works. So that's how, you know, that's what the calculation yields. You know, but so just remark this very beautiful similarity with the matrix model. When you exchange matrices with colored partitions, you exchange the operator U with the operator V and the operator V with the operator U. Okay? So it's a completely different formalism. Okay? Colored partitions have nothing to do with matrices. So it's different, but it has some very beautiful formal similarity, exchanging U, V, and etc. So you have to compute these objects. Okay, I cannot explain you how you do that, but you can do. Okay? And in particular, so you will have generating functions R of Z and A and S of Z and A, okay, that you compute. These functions have nothing to do with the R and S here. They're not the same function. I'm using the same name. They're not the same function. Here, S and R depending on the S's, on the filling fractions. Okay, and so they are completely different functions. Here you don't have filling fractions. Instead, you have A's. So they are completely different functions. In particular, to give you just a flavor of what's going on, here, S of Z was identified with the resolvent of the matrix model. So it means that it was satisfying a quadratic equation. So this S of Z was defined on a hyperelliptic curve. Here, this S of Z has an infinite number of sheets. It doesn't satisfy any algebraic equation. Okay, it's a completely different object. Okay? So just to give you a flavor. So these functions are really completely different. But you just compute them by summing up over these colored partitions. Now, the last step is, of course, to tell you what is the A. What are the values of A that give you the answer in the gauge theory? So essentially, I have to find a superpotential for the A's that do the same for A as what was doing Digraph-Vafa superpotential for the S. Okay? And so that's what I call the microscopic superpotential, but that is very easy to derive. That is very easy to derive. So there are many ways to derive it. Okay? But there's at least one very easy way. It's just to use some R symmetry. In theories, when you have R symmetries, the superpotentials are always given, and that's just the word identity associated with the U1R, by something like this. So probably, well, up to some, probably something like this, up to some factors. I mean, that's just a U1R word identity. So that will just tell, in this particular case, that this is just the average with respect to color partition of the trace of W of X. Okay? That's just U1R. So this is actually easy to construct, since we know the trace of W of X. So that would be sum of GK UK plus 1 over K plus 1. And this UK plus 1 were given here, as a sum of a color partition. So everything is perfectly explicit here. I can compute that explicitly. There's no problem at all. Now the theorem is as follows. So now what is happening? So you have this microscopic superpotential, off-shell object. What is the beautiful property of this object? The beautiful property is that the equation dW microscopic over dI equal to 0 have some solutions. There's not only one solution, you have a discrete set of solutions. And the theorem is that the set of solutions is in one-to-one correspondence with the full set of vacua in your theory. Okay? So that's something that no other superpotential has ever done. Let me remind you, for example, what the Digraph-Vafa superpotential was doing. The Digraph-Vafa superpotential, you had a UN gauge theory broken to U1 and 1 cross U and R. These were called the so-called R-cut vacua. And the Digraph-Vafa superpotential was depending on R variables. So for each value of R, you have a different Digraph-Vafa superpotential. And that was actually the main difficulty with this formalism. The point is that it's only in a Coulomb vacua. So in the Coulomb vacua, this means that you break completely to U1 to the N, that this is weakly coupled. So only when R equal N, the Digraph-Vafa superpotential can be computed from first principles. But for all the other vacua, in particular for the vacua where you don't have any gauge symmetry breaking, so similar to pure N equal 1, this is completely strongly coupled, and the Digraph-Vafa superpotential for this particular case is completely strongly coupled. You cannot understand it. Okay? And whatever superpotential you have in the literature, they always deal with some particular subset of vacua. Typically here the rank is fixed, so the number of factors here must be fixed. Sometimes even more things must be fixed. And so that's why you cannot really compute them. Here, I have only one guy, okay, the microscopic superpotential. It's defined in the A plane, only one function, not a large number depending on whatever rank or whatever other things. There's a regime in A space where everything is weakly coupled, okay? And in this region, I can certainly compute, and that always exists again, because A is just external arbitrary parameter, okay? So I'm choosing to go there. This is an open space, an open set in A space, where instanton calculus apply, and I can compute this exactly. And the radius of convergence of the instanton series is finite, so this is the ball I'm representing here in A space. I computed that. Since it's an analytic function, I know it everywhere, just by analytic continuation. Then I'm doing this extremization problem, and I'm studying carefully what these equations are. Then I will find several types of solutions. Some of the solutions, some A star, will be inside this ball. The A star inside this ball corresponds to the Coulomb type of vacua, okay, which are weakly coupled, and so everything could be understood on shell directly doing instantons. But then I also find a lot of other solutions that are outside this ball. These are the confining solutions, if you like. These are all the vacua that are strongly coupled and that could not be understood. Okay, so that's how the formalism works. But of course, this W of A, I know it exactly because it's analytic. If I can compute it in this ball, I know it everywhere. So I can reliably compute the saddle points outside the ball. That's how it works. And you can do it precisely, and you find all the vacua. So at the same time, you find all the values of R that are possible. So for example, for U3, you will find the U3 vacua, confining vacua. You will find the U2 cross U1 vacua, and you will find the U1 to the cube Coulomb vacua all at the same time as solution of these particular equations, all at the same time. Okay? So it's a completely general solution of the theory that you've obtained with these colored partitions. So now the natural question you want to ask is, but is that anything to do with the matrix model? It's absolutely not trivial, that extremizing is the same as the matrix model. So what is the statement? So what is the theorem that you need to prove to finish essentially the proof of the open-closed string duality in this case? It's complete proof of the open-closed string duality for the chiral sector. So what do you have to prove? Well, you have to prove that the R function that you were computing in the matrix model when S now is equal to S star, so on the saddle points of the digraph alpha superpotential, are equal to the R function, or so let's call this M matrix model, are equal to the R colored partition, now when A is A star. And the same for S. That's what you have to prove. Okay? So the functions were completely different objects when S and A's were arbitrary parameters. But on their physical, what we believe are their physical values, they must coincide. So that's what you have to prove. So here, we know, because this is just by construction, this is the result for the gauge theory. I mean, we've just computed directly the gauge theory path integrals. Here, it was not clear. I mean, there were a lot of assumptions. But if you prove that this is true, then you win. And that mathematically, I think that these are really incredible identities, right? I mean, on the left-hand side, you compute with averages over matrices, On the right-hand side, you compute with averages over colored partitions. And the statement is that they give the same on shell when both formalisms are on shell. And so that's the proof that is included in the paper. And just to finish, you give me just 3 minutes. I just give you an idea of what the proof, how the proof is made. And the best way to present it is just try to understand now the anomaly equations in the colored partition formalism. In the colored partition formalism, the anomaly equations are absolutely non-trivial. They're not natural at all. They were trivial in the matrix model formalism because they were just the loop equations of the matrix model. So in the matrix model, somehow they're just given, for free. In the open string point of view, they are very highly non-trivial. So what this amounts to, is to do what people have done at one loop, to generalize it to arbitrary instanton number, if you like. And to prove that these nonlinear anomaly equations that correspond to these nonlinear variations of the fields remain valid in this sense of the non-perturbative anomaly theorem. And that works. So the result is what? The result is that you can define, the result, of course, is very natural. You can define non-perturbative operators, Ln and Jn, okay, that are of this form. So they are differential operators in A space. Sorry. Okay? And these guys have the following property. Ln acting on the microscopic superpotential that I've been discussing before just gives the anomaly polynomial as a function of A. So that was, if you remember, sum of gk uk plus n plus 1 minus sum of lambda k vk plus n plus 1 minus 2 sum of uq1 vq2, okay? Where now all these functions are the guide that you have, in the instanton formalism, in the colored partition formalism. So all these guys are depending on this off-shell variable A. So this is exactly the realization in the gauge theory of what I was telling you half an hour ago. In the matrix model, this is a loop equation. It means that the loop equation comes from the variation of the free energy of the matrix model. But that's with an infinite number of variables, etc. How do you understand that in the field theory? Exactly this way. This is like the free energy of the field theory. This is the quantum gauge theoretic version of the Virasoro operator. And you have this formula that gives you on the right-hand side like the loop equation of a matrix model, but no, it's exact. You don't have any correction. That's an exact formula. Highly non-trivial and unnatural in this formalism with colored partition. If I didn't know that I wanted to get it, you would never be able to think that such operators exist that acting with this gives this simple quadratic form. It would be impossible, just because you know that you want to prove it, that you managed to do it. In the open string formalism, it's a completely unnatural thing. But it exists, and you do it. So of course, you have the same for the Jn. Okay, so Jn acting on Wmic is Bn of A. Okay, so the other anomaly polynomial, and you define that. And then you have quantum version of the super Virasoro algebra that are extremely complicated. So I don't have time. I can take you a little bit what it is. I mean, they are very nice algebra of operators defined in some very nice way, but they are not closed at all. So they don't close on the L's. Okay, so if you want to compute, for example, ln lm, that would be, of course, so the first term would be this. But then you have a bunch of corrections, and these corrections cannot be expressed only in terms of the J's. So to have a closed algebra, you have to enlarge enormously the set of operators but you can do it. You can construct exactly what it is. And so these are the non-perturbative gauge-theoretic Virasoro operators. The last comment, how do they act on the variable u's? I was telling you before that all the simple approaches didn't work because it was assumed that the LMs acting on the operators were given element in the chiral ring. Okay? Here, it's not the case. How does it work? So of course, you still have these plus corrections that depend on A. So what happens is that this ln, when they act, of course, give perfectly well-defined functions of A. But A of U is not well-defined. So all the U of A or the V of A, the operators are well-defined functions of A, but you cannot inverse these relations. This is related like to the monodromy in n equal 2, if you like. Okay? So these are perfectly well-defined objects as function of A's, but if you want to express everything in terms of the chiral operator, you get multi-valued function on the chiral ring. And that's why it's so complicated, to guess the result from scratch and use Ves-Zumino. It's impossible. But now with this color partition, we have everything explicit. Of course, because you have this, the Ves-Zumino consistency conditions associated with the quantum algebra of the L's and the J's are automatically satisfied. Because the Ves-Zumino consistency conditions are just immediate consequence of these relations. Okay? But they are very complicated, written in terms of classical variables. You have a lot of quantum corrections, very complicated quantum corrections. Okay? So this is the anomaly equations. Of course, on shell, since these ln's and jn are first-order differential operators, okay, this is 0 on shell. But not so for arbitrary value of A, this is not 0. But for A equal A star, this is 0. And then you find that these guys satisfy the same equations as in the matrix model, but on shell. And so that's the main point of the proof of these relations. Then you can work everything out in details and show that it works. Okay? So I'm just concluding and I think this is a very nice duality between a formalism based on colored partitions that is a completely first principle approach to n equal 1, and this kind of 5-year-old formalism based on matrices that we understand best when we talk about closed string theory, because that's a closed string formalism. And here we see that both are equivalent. And the fact that you have two such different starting points, matrices on the one hand, colored partitions on the other hand, that yield the same result. I mean, it's just a beautiful, example of how an open-closed string duality works. For any gauge theory, we always expect, for whatever question you're asking in gauge theory, we always expect to have two completely different starting points to answer the question. One would be the open string, like first principle approach. We call it first principle because the gauge theory were defined first in terms of matrices and the Young-Mills formulation. And the other way would be using closed string theory. These are two different approaches, two different starting points that are supposed to yield exactly the same result. This is exactly what we've derived here. Okay, so this is just the meaning of these equations. Okay, thank you, and sorry for being a bit too long.
Probably we better go.
I think
Yeah.
I was going to say, I think that's really good lectures. Thank you. I think we'll have failed to beat the 1 o'clock rush for the